Alright, the periodic table. We're going to learn how to read the periodic table. We're going to learn how the elements are organized. What does the word period or periodic mean? What does the word periodic mean? Occasionally, you're in the right direction, but no. If something occurs periodically, what's it doing? You're close. It means it repeats over and over and over and over and over. It occurs in a regular pattern. So a periodic table is a way of organizing the elements such that their properties repeat over and over and over again. So, no, it's for chemistry. I need to give them a blank periodic table that doesn't have the notes on the back. So, Dmitry Mendeleev is credited with discovering a pattern of the elements. He was the first person who organized them into a table and noticed that elements, when arranged by similar properties, that the pattern was periodic, meaning they repeated every 7 elements. Yes?
Do you know what parafood is?
Yes.
Well, I mean, it can be like disk drive and all that. You put it on the disk drive and see the little outlines of it. You put it on a thing and see the code on the Bible.
So, why do you think the elements repeat every 7 elements? So, yeah, I've got periodic tables.
Wait,
What? Be quick. So, the rows are called periods. The columns are called groups. If we ignore the middle transition metals, we can see that we have 1, 2, 3, 4, 5, 6, 7, 8. So the pattern repeats every 8 elements. Whenever he came up with the periodic table, he noticed the pattern repeating every 7. Thomas, keep your mask on. Why do you think he noticed a pattern that repeats every 7 than 8? You're close. Very close. So, where are the gases? What are these gases called? Noble gases. Why are they called noble? Because they're stable. What does the word stable mean in this context? They don't react. If they don't react, how would you be able to define them? You can't mix any chemicals with them to extract them. Back then, they had no clue the noble gases existed. There was no way to do chemistry and discover them. These gases do not react. So back then, he had the periodic table without the noble gases because he couldn't have discovered the noble gases because they did not react.
So how did we find out?
We got more advanced technology to where we could actually measure the mass of atoms more precisely. Back then, how they did it is they had like salt. Salt was sodium and chlorine. And what they could do is measure the relative size of the sodium part versus the chlorine. We could break them apart. So what we could do is we can measure the mass of salt. We can then melt the salt into a liquid and run electricity through it. What would happen if you run electricity through molten salt is the chlorine will be broken off. The chlorine will float up into the air and you'll be left with pure sodium. Now, if you took the mass of the sodium that's left and compared it to the mass of the salt, you can figure out how much the sodium weighed versus how much the chlorine atom weighed. So that's how they were able to figure out and do chemistry back then, is they could figure out, well, sodium weighs less than chlorine. In fact, if you look at the periodic table, they figured out that the mass, chlorine is about 35, and sodium is about 23. So the chlorine was significantly larger than the sodium atoms. So he discovered that they were repeated every 7 because he didn't know about the noble gases. And he named it the periodic table of elements. So what is the periodic table? It represents our understanding of the structure and usefulness of atoms that have been identified in our environment. They are organized based on similar properties. All the noble gases don't react, so they're in the same group. They're all in the same column. So it contains over 100 different elements. So what do the numbers and the letters mean? Yes.
And then the numbers below the letters are how much it weighs.
Yes. And the HE, even though it looks like it's a letter, is technically called a symbol. It just uses the same symbols as the Latin alphabet. So the symbol for helium looks like an H and an E next to each other. You should treat that as a symbol, not just letters. So let me pull up the ancient periodic table and show you why we call them symbols. And aren't you so glad you don't have to memorize all these symbols? Sodium. So that's sodium. That's calcium, I believe. Some of these aren't elements. They weren't able to break it apart. For example, ammonia is NH4. So that's nitrogen with hydrogen. But they all had unique symbols next to them. Luckily, we changed that around and not did it. And Cody, keep your mask on. So, the element name will be at the top. The atomic number, and you are right, the atomic number is the number of protons. Then we have the element's chemical symbol, yes? Not divided, you subtract. So if you subtract 4 minus 2, you see that as helium has 2 neutrons. You have to round that number to the closest integer. The reason why it's a decimal point is because there's different isotopes. Isotopes have different number of neutrons. And so the last one is the atomic mass. It is the average mass of one atom of the element of all. It's the average mass of all the isotopes. So we have different isotopes. We have like carbon-12. Carbon-12 has 6 protons, 6 neutrons. Carbon-13 has 6 protons but 7 neutrons. Carbon-14 has 8 neutrons. And not over 90% of all the carbon atoms is carbon-12. So most of all the atoms are of one isotope. there are a few that are have different isotopes. So as you go to the right, you'll notice that that the mass increases, and as you go down, the mass increases. There is an exception to this. Beryllium and iodine are different, but for the most part, we'll ignore any exceptions.
This question, and it made sense to me. Probably never will. If the number in between the symbol and the whatever between the symbol and like just the top and cover. How are they numbered perfectly?
What do you mean?
Like you got like okay, so like you know how the one over here
Mhm.
how many ones are
Yeah.
how is it so perfectly aligned? What's 1, 2, 3, 4, 5, 6?
Because that's how we aligned it.
But how can you I thought that's how many protons it is.
Mm-hmm. We organize it by the atomic number.
Exactly, but doesn't make sense because
Okay. Let me do a very good example to you.
my brain hurts talking about this. Just like when I think about what's happening after that.
All right. I have a jar of 3 marbles. I have a jar with 1 marble. And I have a jar of 2 marbles. I can put the jar with 1 marble here, the jar with 2 marbles here, and the jar with 3 marbles. And your question is, how have I perfectly aligned these so they go in order?
That's what I meant.
That is exactly what you meant. And then if I had a jar with 4 marbles, then I'm going to put it right here.
I just find it odd that each element has exactly the amount of protons just to like have one that goes to one. Don't you think they?
Oh, that there should be some that skip. So, like for example, maybe there is no jars with 2.
How is there one that doesn't have the same amount of protons or whatever?
So it depends on stability.
My brain hurts.
So I'll show you an example.
Things are hard to
Look at here. There's a blank spot in between UUB and UUQ. That's because once you get into the U's, those are man-made, and we weren't able to create a element in that spot, so it becomes a blank. There were blanks, like you were saying, until we discovered them. A lot of the bottom elements are radioactive and don't exist for long. All the elements up to lead are stable.
I just find out there's an element for each.
Yeah, so you're saying why is it there blanks in the periodic table?
Hurts my face.
It's just you can add enough neutrons to make it stable, is the answer for lighter elements.
This color's answer was always, well, it's just how it is. That doesn't answer my question.
So the answer to your question is, in nuclear science, using quantum mechanics, you can add enough neutrons into the nucleus so that the nuclear force will bond the protons and the neutrons together such that it doesn't decay and fall apart. It just so happens that for most elements, you can find a certain arrangement of neutrons and protons that is stable and it doesn't break apart. Once you get into, for example, radon, radon is radioactive. The neutron will break apart and eventually we won't have any more radon. Uranium is actually somewhat stable. I can have a chunk of uranium on my desk, just fine.
Isn't that radioactive?
It's radioactive, but its half-life means every atom will basically stay an atom for 1 million years. So it takes about 1 million to 100 million years for half of a sample to disappear, to decay. Because we measured it. So the periodic table is arranged like a big grid. The properties of an element can be predicted from the location on the periodic table. There are rows and there are columns. Each row and column have a different meaning. So we can also divide the table up into metals, metalloids, and nonmetals. So let me show you how you can divide this up. So pay attention. So starting at boron, we're going to make a staircase. We're going to look above the staircase and below it. Aluminum, we're going to call a metal. Aluminum is a metal, right? So we'll call it a metal and won't color it in. Everything else, above and below, above and below, above and below. I usually classify polonium as a metal and astatine as a non-metal. I would usually stop here, but about 40 to 45% of science communities would classify this as a metalloid. But these are your main metalloids. In this class, I'm not going to ask, I don't think I asked about this. You can call it a metalloid if you want. I'll have to fill it in. And I'll even slightly fill this one in. So above and below, it's a metalloid, except for aluminum. Aluminum, I will most definitely say, is a metal. So what is a metalloid? A metalloid has properties like metal, and Cody, keep your mask on, and it has properties like nonmetals. Everything to the left of this line, everything to the left of the metalloids are metals except for hydrogen. Everything else is nonmetals. So the nonmetals are going to be the right side. The bottom left is going to be your metals. So what are some properties of metals? Metals are shiny. Metals are usually solid at room temperature. What's the only exception?
Mercury.
Mercury is the only metal that's a liquid at room temperature. Gallium is a solid at room temperature. Does anyone know what the exact temperature of room temperature is defined as? Close.
69
Close?
70.
Nope, too high. 68. 20 degrees Celsius or 68 degrees Fahrenheit is what we define as room temperature.
Is the room temperature here enough?
It's a little warmer than room temperature. And y'all keep those masks on. Thomas, Michael, wake up. Thomas, lift your head up and keep your mask on. Gallium melts at about 85 degrees Fahrenheit. So if you were to put it on the desk, it'd be a solid. But if you were to grab it and hold it in your hand, it'd melt. Their internal body temperature is around 98.6, or outer skin is usually around 90 degrees. And it can be colder. It can be warmer. So your hand should be almost about like 85 to 90 degrees. Metals have a high conductivity. This refers to both thermal and electrical. Most metals can be flattened and do not shatter. That means they're malleable. Non-metals are not shiny. Non-metals are mostly gaseous at room temperature. Can y'all think of some exceptions to that? Carbon, sulfur, phosphorus.
I don't know. I'm just gonna take a guess and say
argon. Argon is a noble gas.
I don't know what argon is. I just know it's a gas. It could be or something.
Non-metals are usually poor conductors of electricity and heat. There are exceptions. Carbon can conduct electricity. Chlorine. Chlorine mixes with water to form hydrochloric acid in your lungs. Mustard gas is something different. Non-metals are usually brittle. Think about your pencil lead. How brittle is your pencil lead? How easy can you bend it into a circle without breaking? And what would happen if you take your pencil lead and hit it with a hammer? It'll shatter. So it's not malleable or ductile. Metalloids have characteristics between metals and nonmetals. Metalloids are usually solid at room temperature and can act as semiconductors. Your phone has a combination of silicon, germanium, and arsenic. Silicon is used heavily in conductor or phones.
Don't you use silicon?
Cody, keep your mask on.
Don't you use silicon to make silicon?
So silica is like glass. So silicon dioxide is sand, and you can.
How many elements can you inject without dying?
I don't know.
That's not been doable right now.
So each horizontal row of a table is called a period. We'll learn about this later, but you can think of, it's wrong, but it's a good model. You can think of the electrons as planets orbiting around the nucleus. And they orbit in certain energy levels. So the orbits are called energy levels. Groups, also called families, are the columns. We're going to mostly be ignoring the transition metals in the bottom two rows. So there's, that says 6 groups. How many do y'all count? Oh, wait. No, never mind. I'm looking at the G as a 6. It just says groups. So there's 18 groups in total. The elements in the group have the same number of electrons in the outer energy level. Groups are often grouped together to form families because of their similar properties. So, the first period all has one energy level, one orbit. Everything in the second period has 2. Everything in the third has 3. Everything in the fourth has 4. Everything except for helium in the 8th group has 8 electrons on this outer one. Helium only has 2. So helium only has 2 here. Everything else on the last column will have 8 electrons on the outer one. These would have 7 on their outer one. So let's look at. So fluorine has 2 orbits. And because it's in this group, it'll have 1, 2, 3, 4, 5, 6, 7. Everything in here, so looking at oxygen, would have 1, 2, 3, 4, 5, 6. Coming over here, let's look at lithium. Lithium, so everything in this one would have 1. So hydrogen only has one, so that's hydrogen. Lithium has two because it's in the second period, but it has one electron on this outer one. Everything in this one, so beryllium, has two energy levels. Since it's in the second group, it has two electrons on the outer energy level. We can ignore the transition metals for now. There are exceptions. So, you probably know a family with several members who all look alike. The elements in a group or family in the periodic table often but not always have similar properties. Although you are not expected to know their names, in this class you will. You need to learn their names. So periods go down, groups go to the right. There is one exception, or I should say two. And Thomas, lift your head up and pay attention. No. So the two exceptions we're going to look at is hydrogen and helium. So the properties of hydrogen doesn't match the properties of any single group. So it is set apart. It's by itself. We put it above group 1 because it has only one electron in its outer energy level. The first group is called the alkali metals. So it's the first group excluding hydrogen. This will include lithium, sodium, potassium, rubidium, cesium, and francium.
So, Mr. West, think about number 1 and number 2, and them being highly active with each other.
The metals usually don't react with themselves.
No, helium and hydrogen.
No, helium doesn't react with anything. The next one is the alkali earth metals. So that's everything in group 2. Everything in the middle is called the transition metals. Then we have the boron group. The first element in the boron group is boron. Then carbon group. Then nitrogen group. Oxygen group. And this one, we do not call it the fluorine group, we call it the halogen group. So halogen includes fluorine and fluorine. And lastly, we have the noble gases. And at the bottom of the table is the rare earth. So yes, they are rare because they're all radioactive. Yes? Be quick. Because Elena wasn't here.
Oh, I was not going to say nothing.
So most periodic table elements, so there are only two liquids. That's mercury and bromine. At room temperature, they're the only two liquids. Used to. The only gases are the noble gases plus some of the diatomics. Hydrogen, nitrogen, oxygen, fluorine, and chlorine. So it's the noble gases plus those four. Everything else is solid. Y'all lift y'all's head up off the table. So, atoms are often take, give, or share electrons with other atoms in order to complete the set of electrons. Besides hydrogen and helium, all the elements want to have eight electrons on the outer shell, or outer energy level. Hydrogen and helium only want to have two. Everything else wants to have 8. So it's how close we can get to having a complete shell. Everything on the left side wants to get rid of their few electrons to have a full shell. Everything on the right wants to gain electrons to get a full shell. So if we look at the reactivity, as you go to the left, you get more reactive. As you go to the middle, you get less reactive. And as you go to the right, you get more reactive, excluding the noble gases. Yes. So, which is more reactive, sodium or magnesium? Sodium, because it's to the left. Which is more reactive, oxygen or fluorine? Fluorine, because it's to the right. And carbon is probably the most neutral, I would say. It's in the middle.
What could you get carbon to react with?
It reacts with a lot of things. We're carbon-based life forms. It's just that it can go either way. So, carbon has 4 valence electrons. 4 electrons in its outer shell. So it can either gain 4 and have a complete 8 electrons, or it can lose those 4 to have a complete outer shell. So it can lose the entire outer shell, and the next shell below it is full already.
So, and I have 4 valence electrons.
Yes.
So that means it will start 2 will go to the first one, and 2 will go to the second one.
Mm-hmm.
Maybe 6 that you can
Yeah, you can go to the...
The only reason I know what carbon life forms is because Rick and Morty talk about it.
In general, elements located on the left of the periodic table are the most reactive metals, and the least reactive metals are the ones in the middle. So let me show you the alkali metals.
There are 6 alkali metals.
Alright, y'all pay attention. Alright.
There are 6 alkali metals: lithium, sodium, potassium, rubidium, cesium, and francium. They're all soft metals which can be cut with a knife. In air, the elements quickly become coated with compounds that form on the metal's surface. Here, for example, is lithium. When we slice it, you can see the metallic luster, but the black coating quickly reappears. Sodium is kept under oil to prevent reaction with air. Again, when we cut it, the metal's surface can be seen. But this time, corrosion occurs even more quickly.
So it loses its luster, its shininess, as it reacts with oxygen.
With the next alkali metal, potassium, the corrosion in air is so quick that it's hard to see the metallic luster at all. As we go down the group, the elements seem to react more quickly with air. Now let's see another reaction of the alkali metals.
There's a chance that if it gets moisture in it, when you cut it, it could just immediately catch on fire, sending molten metal that will blow up on your skin. If you have a chemical that burns and explodes on your skin, a fire extinguisher isn't going to repair your skin that's blown up.
The reaction with water. We'll start with lithium. The metal floats on the water and reacts with it, giving off hydrogen gas. Now for sodium. The same sort of thing happens, although the reaction is a bit more vigorous. All the alkali metals react with water in the same way. Let's see an equation for the reaction. hydrogen gas is produced, and the metal dissolves to give an aqueous cation with a single positive charge. Now for potassium. This time you'll see a flame. The heat given out by the reaction is produced so quickly that the hydrogen gas catches fire. It burns with a lilac flame.
So it's producing hydrogen. It's producing hydrogen gas and a lot of heat. Once you get to potassium, that heat is enough to catch the hydrogen gas on fire.
The next element is rubidium. This time, we put a safety screen between us and the reaction. You can see that things gradually become more terrifying as we go down the group. Let's try cesium, our fifth alkali metal.
What was that?
Cesium. Later. Probably not today.
I like seasoning to do that.
So as we go down, we increase in reactivity.
Don't bring that back.
So everything in the same group has the same valence electrons. Electrons, or valence electrons, are the electrons on the outermost orbit. Are only the electrons on the outermost energy level. Another name for energy level is shell or orbit. Orbit is strongly discouraged because there's a concept called orbital. Everything in the same period. Periods all share the same number of energy levels. Again, that means same number of shells or orbits. So, for example, if we were to go down the group 1, so group 1 is hydrogen, lithium, nitrogen, potassium, and so on and so on. So this has one orbital with one electron. This has two orbitals with one electron on the outer. This has three orbitals with only one electron on the outer one. And I'm not going to continue drawing all of these. One on the outer one. So 1, 2, 3, 4, and so on. There's electrons in here too. So beryllium, so looking at group, let's do group 7. So we have fluorine. Fluorine would have 1, 2, and this would be 17. Also called 7A. So it has 7 electrons. And 1, 2, 3. So chlorine has 3 orbits, or 3 energy levels, but they all have 7 on the same. And likewise on the next one. So they all have 7 electrons on the outer one. Looking at a row, so a period, let's look at period 2. This is lithium. Lithium has 2 energy levels and only has 1 electron. Let's go to the next one, beryllium. It has 2 energy levels, but now it has only 2 electrons. Then boron would have 3. Carbon would have 4. Nitrogen would have 5, and so on and so on. So they all have the same number of energy levels. Y'all quit doing that and put those up or throw it away. Wherever you're putting in your mouth. Throw it in the garbage. Go throw it in the garbage. You shouldn't be eating in class. Go throw it in the garbage. Put it in the garbage. Yes, go spit it out or I'm writing you up. Alright, we'll continue this tomorrow and learn more. But y'all think y'all got this?